What up, calculus students? Let's do this limits homework. So, limits, building block of calculus, understanding that we can get infinitely close to something, pretty much be at the location, but not essentially like right at the location, just to the left or just to the right, but so close you're essentially there. We like to focus on, let's focus on an easy point right now. So we're going to focus on x values. This is a function, h of x. Let's make sure we understand that with functions, you have x values that get inputted into the function and it outputs y values, okay? So h of 0, when x is 0, h of 0 is what is the outputted y value, the y value being the point above or below the x coordinate of 0. So at 0, the y coordinate's 1. We say h of 0 is 1. Okay? Now, this is an easy point because there's nothing crazy going on here. We just have the point, and to the left and to the right of 0. So this reads, what's the limit as x approaches 0 from the left? To the left of 0, which is right here, I'm still going to be getting really, really close to this y coordinate of 1. As I get closer and closer to 0, I'm getting closer and closer to the y coordinate of 1. So this is a situation, and we'll talk about it more next class, that the function is continuous. There's nothing crazy going on. And the limit and the function value would agree with each other. To the left, we're approaching 1. To the right, I'm also up here, but I'm approaching 1. And that's why, since the left-hand limit equals the right-hand limit, the limit in general exists and it equals that value. Now, let's go and look at the interesting point, x equals 1. Okay, so when x equals 1, what is going on? Well, there's a lot of crazy stuff here. We got open circles, we got closed circles. Hopefully our work in our notes with our piecewise functions where everything was expressed, you can kind of see when x equals 1, h is telling you use this y coordinate here, 1, this closed circle 1, okay? But if you went a little bit to the left of 1, we're talking about 0.99999. That's what we mean by being infinitely close to 0.9 repeated. If we're at 0.9 repeated, we would be using this function. This piece of this function, this part, is used when x's are less than 1. And this piece, if we're to the left of 1, we're up here getting closer and closer. As we get closer and closer to 1, we get closer and closer to this y coordinate, which is 3. And we have this open circle location to be if we were to use this piece at 1, it would equal 3. So that kind of open circle helps you. If I'm to the right of 1, I'm using this piece. This piece is used for x is greater than 1. So if I use 1.001, if I plug that in, 0 is repeated, I'm going to get really, really close to 1, but from this side. And I see my y coordinates are getting really, really close to this location, which is at 0. If your left-hand limit and your right-hand limit are not the same, the limit does not exist. I don't care about the function value at all when I'm making my decision of the in general limit. Okay, it's very important when we look at other situations, when we go to 2. Let's start with the easy point at 3. X equals 3. Let's look at 3. X equals 3. Here's x equals 3. Y equals 0. Y equals 0. So g of 3 is 0. To the left and to the right, I'm approaching that same value. We will say our function is continuous because the limit agrees with the function value. You'll learn that next class. Now let's look at some trickier points at 2 and at -1. Let's start with -1, okay? When x is -1 to the left, now this is important. What's -1 to the left? That would be something that's a little bit bigger than -1 on the negative side. So -1.0001. Okay, so I'm over here. Now, if I'm over here, I'm using this piece. This piece is used when x's are less than -1. So If I were to use this piece at -1, it would give me this y coordinate at -1. That's kind of telling me that as I get closer and closer and closer to -1, these y values are going to get closer and closer to this y value of 2. Now, if I'm to the right of -1, like -0.99999, okay, here's -1, here's to the right, I'd be using this piece. I'd get closer and closer and closer to this closed circle. Well, we're approaching this y coordinate, -1. And since we have a closed circle here, that's our function value. Okay, cool. However, the left-hand limit and the right-hand limit do not agree with each other, so this limit does not exist. If I were to look at x equals 2, this is a point that everybody messes up on. Now notice there's a closed circle up here. So if I was looking at the piecewise function, it would have like a little extra line. You know, if I had the piecewise function for g of x, it would have some extra little line that when x equals 2, use the y coordinate 3. So when x equals 2, use the y coordinate 3. Okay? But, you know, for all x's except for 2, between -1 and whatever, infinity, we're going to use this piece, whatever this is, whatever the equation is for it, okay? Which means if I'm plugging in something like 1.999, 1.999, I'm going to be approaching, you know, what this y coordinate would be, because these are all the values for this other piece. Like this is like, you know, the curve, this curve I'm using for x's not equal to 2. Which means like if I plugged in 1.9999, I'd plug it into this. Plugging in 1.999 repeated is going to give you essentially, remember like the calculator will just tell you like, yo, just round it to 2, please. But it's like, no, we're going to be approaching, we're going to get infinitely close to this y coordinate, which is at 1, if we're to the left of 2. And if we're to the right of 2, we are approaching this y coordinate at 1. Which means even though we have a point somewhere else, if this number agrees with this number, that's the limit. That's the only thing I can tell you. And everybody messes up on this. They think like, oh, the limit doesn't exist or something. It's like, just look at the left and the right. If they're the same, that's what the limit is. Don't make mistakes on that. Okay, let's look at -2. Now at -2, I don't have a point above or below it, which means at -2, f of -2 is undefined. I don't have a point that I can go to and say, like, if you plugged in -2, you would get this. However, if I plugged in -2.00001, something like right here, -2 to the left, I'm down here at these y coordinates. I'm close to the y coordinate -2. That's a y coordinate. If I'm to the right of -2, I'm still down here at these y coordinates at -2, which means my limit's -2. I'm approaching the value of this open circle. I can't plug in -2. It's undefined, but I can plug in things very close to it and get a value. And the values that I'm going to get are going to be very, very close to -2. If we look at 1, we got like a jump here to the left of 1. I'm down here at this piece. To the right of 1, I'm using this piece. To the left of 1, I don't care about the open or closed circles. You can just be like, I'm using this piece for x is less than 1. For x is less than 1. If I were to plug in 1 into this piece, I would see I'd get a y value of -1. That's like plugging in 0.9999999 into whatever this equation is to get this value. If I were to plug in 1.00001, I'd be up here, getting close to this y coordinate 2. The left-hand limit does not agree with the right-hand limit. That means the limit in general does not exist. F of -1. Oh, -1's right there. F of -1, that's 0. That's a point there. And the limit would be 0 too. I didn't add that third line. F of 1, if I looked at the piecewise function, like this piece for f of x. Whatever this equation is, it would be like, that equation is used for x's greater than or equal to 1. So that means I would plug in 1 into this piece. This piece would give me the y coordinate of 2. We'll get to piecewise functions right now, where it's like, hey, I'm not giving you the graph. I'm just going to give you the equations that produce the graph. Okay? This is how we started it off in class. So pay attention to what's going on. I'm using this piece for x's up to 1, but I'm not including 1. But I'm going to use it for 0.9999999. I'm going to use this piece for all x's greater than and equal to 1. Okay, so if I ask you what's f of 1 if you plugged in 1 here, you'd say, well, I have to use this piece at 1 if I plug in 1 to get my y coordinate. 1 minus 1 is 0. Cool. Got that? But if I were to plug in 0.99999, that's a value that's less than 1. Now I'm talking about using this piece. Now here's where it's like a little bit theoretical. Remember in our calculator, if you just keep typing in 0.9999999, your calculator's like, dude, it's just 1. Or if you're like 2.99999, they'll be like, yo, it's just 3. Because you're so close to it, we can essentially feel like you're there, okay? This is the concept of getting infinitely close to approaching. Don't plug in 0.99999 into this, because you're going to get a value that's essentially the exact same you're going to be infinitely close to if you plugged in 1 into this. And if you plugged in 1 into this piece, because we're using this piece for x is less than 1, we get negative 2. Okay? If I go to the right of 1, let's switch. Ooh. If I go to the right of negative 1, I'm thinking about using 1.00001. Well, I use this piece. Now, again, if you just keep typing in 0.00001 and press enter, your calculator is like, dude, you're just pretty much giving me 1 here. So don't plug in 0.00001 into that, because like you don't want to try to square it and you don't have a calculator. You know that it's essentially, it's the same. It's going to give you a value that's like infinitely close to what you would get if you plugged in 1. That's why we will say we are approaching 1 squared minus 1, which is 0. The left-hand limit and the right-hand limit do not agree with each other. I don't care that this agrees with each other. I don't care that I have a point. This limit does not exist. Now, here come some tricky ones. What's the limit as x approaches 2 from the left? Okay, well, maybe you could think 1.99999. Maybe. But we know that's essentially 2. Well, we know, let's change colors, that we use the blue guy at 2. We don't use both of them. So you're not going to like plug it into this one because it's to the left. It's not 2 from the left means use the 1 for x is less than 1. No, it's like, which function do we use for 1.9999? This guy. All x is greater than or equal to 1. Use this guy. So I'm going to plug in 2 into that guy. Not 1.999. Again, it's like, it's going to give you a y coordinate that's going to be essentially the same. It's approaching this value. 2 squared is 4, minus 2 is 2. Got that? Now let's look at 0 from the right. It's not that it's from the right, use this. It's at it's 0.0000 repeated 1. Okay, at 0, we don't use this piece. We use this piece when x's are less than 1. So I would plug in, essentially infinite zeros followed by a 1 into this. You plug in infinite zeros followed 1 into that, you will get a y coordinate that's approaching what you get if you plug in 0 into this and subtract 3. 0 minus 3 is negative 3. Which brings us to x approaches 3. Okay, it's not saying from the left. It's not saying from the right. But, man, let's think about it. at 3, I'm using that piece. If I'm 3 from the right, I'm using that piece, and essentially it's the same as plugging in 3. If I'm 3 from the left, I'm still using that piece, and it's essentially plugging in 3. So actually, you don't have to worry about the fact that it's one-sided. There's no like checking two sides in here because you're using this at 3, like no matter what. It's a part where we're like continuous. There's no like jumps or anything. So I plug in 3 into this piece. 3 squared is 9 minus 3 is 6. All right, some more. I'm going to kind of go quicker through this. Ooh, what's the limit as x approaches -1? Okay, look, maybe it's easy. Maybe I'm just using one piece for both sides of -1. Nope. Unfortunately, I'm using this to the left of 1, and I'm using this to the right of 1 up to 2, which means I kind of actually need to do a little bit of legwork myself or a little bit of thought. You don't have to show this if you don't want to. But you do need to check the left-hand limit and the right-hand limit. If I plugged in -1 to the left, if I plugged in -1.00001, I'm plugging it into that. If I plug it into that, it's essentially like plugging in -1. -1 squared is 1. Okay, cool. But now I have to check the right-hand limit. Limit as x approaches -1 from the right. Now, -1 from the right is using this piece. X is bigger than or equal to -1. So -0.9999999 repeated. Well, again, don't plug in that because essentially you're plugging in -1, but you're plugging in -1 into this piece. You get 3 times -1, which is -3 plus 4, which is also 1. Now, it's because the left and the right-hand limits actually agree with each other. These pieces actually meet up. Since the pieces meet up, hip, hip, hooray, you have a limit. The two pieces connect. You could say you're continuous there because they connect. Cool. What about at 0? Well, at 0, I'm not jumping from one piece to the other. I'm just using this blue guy. So really, I don't have to worry about -0.001 and 0.001. I can just plug in 0 into this. And I get 3 times 0 plus 4, which is 4. Oop, let's switch to blue so we know we're using that piece. I have to get another color here. Now, at 2, I'm using this guy to the right of 2. And I'm using 3x plus 4 to the left of 2. So this is where it's like, oh, you're using two pieces. Maybe they don't connect. Maybe they do, but you have to check. It's the whole like piecewise, will we jump or will we connect? So you got to do a little bit of legwork for this one. You got to look to the left of 2. You got to look to the right of 2. It's not like the limit as x approaches 0, which is easy. All right. To the left of 2, 3 times 2 plus 4 would be used, plugging in 1.999. But it's the same as plugging in 2. 6 plus 4 is 10. To the right of 2, 11 minus x would be used because these are x's bigger than 2. 11 minus 2 is the same. It would be the same. It would be the value that 11 minus 2.00001 would be approaching. Okay, so we get 9. The left-hand limit does not agree with the right-hand limit, so this limit here does not exist. These pieces don't connect. One's a little bit higher to the left than the other one to the right. If I were to use 3, however, x approaches 3, well, I'm using this piece for 3's, to the right of 3 and to the left of 3. I'm using 11 minus x. So 11 minus 3 is my answer. Okay, I hope this makes sense. It's like, yes, you are thinking about plugging in 3.001, but it's infinitely close to 3. We're using that piece at 3. It's the situation where, like, at 3, we are going through 8. But, like, maybe we don't even see, like, usually when we graph and there's no, like, jumps or anything, we just say, like, boom. And then you're like, oh, yeah, to the right, to the left, I'm at 8. And the value's 8. or continuous. We'll talk about that. All right, this is a good one. For everywhere except for at 2, I'm going to use 3 minus x squared. That's not accurate, but everywhere except for at 2, I'm using 3 minus x squared. Just go with me. So I'm using it everywhere except for 2. So I'm leaving a little space. At 2, I'm using 7. Now, that dot might be right here at that location. I don't know yet. I'm just kind of sketching. But maybe it's not. And maybe if it's not, we can see, like, using an open circle. Oh, like we're skipping this spot on my curve, on my 3 minus x squared, but we're using this spot. So if I ask you, like, what's f of 2? Well, like when x is 2, f of 2 is 7. But I ask you, what's the limit? Well, if it's like, all right, if I plugged in 2 to the left, 1.9999, I'm not going to get 7 because I'm not going to use this. At 1.999, I'm using this. When x is not equal to 2, that means like infinitely close to, isn't equal to, okay? It's approaching, it's close to. I would not say, oh, 7, because it's close. No, it's like, well, you're using this piece when you're infinitely close to 2. So you plug in actually 2 into this piece to see like 3 minus 4, oh, negative 1. So in reality, like my graph is a little bit off. It's looking like that, where that's negative 1. That's 2. I mean, that's still not great. Let's start over. I'm sorry. I don't want to. I always like to be like, oh, you guys get it. And I'm like, no, I can always do just a little bit better. All right. So here's 2. Here's at 2. I'm not using this quadratic. At 2, I am using this point. What are we approaching? You can kind of see. It's like, oh, we're approaching this y coordinates location. To the left and to the right, we'd approach this y coordinate of this at 2, which is negative 1. Plugging in 2.001. I would plug in 2.001 into this. Okay? What's the y coordinate we'd be approaching? Whatever the y coordinate is when we plug in 2, negative 1. Cool. You won't use a calculator on your quiz, but it's good to kind of see what's going on here. So easy ways to like look at things and check values in calculators is to graph. Again, you're not using your calculator on your quiz, so heads up. This is just more for display purposes and for like investigation purposes. And I'm going to show you how to do this without a calculator in a second. So here's the graph of x to the 4th minus 16 over x squared minus 4. And if I plug in 2, go to trace 2. This is an easy way to find y coordinates based on x coordinates. My calculator is like, yo, no, I can't. Y is blank. You're like, what do you mean y is blank? Well, it's like if I plugged in 2 to the 4th, I get 16 minus 16. 2 squared, I get 4 minus 4. I get a 0 over a 0. 0 over 0 is undefined. This is like the non-calculator way of saying there is no function value here. Your calculator of seeing it is like if you plug in 2, you see, hey, at 2, there's no value here. But you can kind of see, like at 2, it looks like we have values there. If you, after pressing trace, go to the left and to the right of 2, you're like, yo, it looks like I got a value there. What your calculator doesn't show is that at 2, there's a hole. Okay, there's some hole that's missing, which means we are going to be approaching that y coordinate. Now, how can we get that? Well, with your calculator, it's nice and easy because your calculator can plug in 1.999. Now, if I plug in too many 1.99999s, your calculator is probably going to round to 2 and then still say, nah. Okay? So you can do sometimes too many, and your calculator is, yo, like you gave me too many 1.999s. I plugged in 2 and I can't plug in 2. But don't go crazy. Plug in a little bit less, and you realize like, oh, my y coordinate close to the x coordinate of 2 is 8. Maybe we can get a little bit closer if we added an extra 9. Don't want to add too many. Yeah, let's get even closer. Don't go crazy. The calculator is like, yo, I eventually rounded 7.999. I said it's 8. We can go to the other side. Again, if you go too crazy and get too close to 2, your calculator gives up and just rounds. They're like, yo, too many decimals. I just plugged in 2. But if you go a little bit less crazy, your calculator actually does plug in that value. It does not round to 2. It says like, all right, I'll plug in 2.0001. You get 8.004. You can see that from the left and from the right, we are approaching this location of this hole, which your calculator eventually gives up and says it's essentially at 8. Okay? So that's how you do it with a calculator. Now, without a calculator, you're like, how do I get this limit? What you'll see is like, well, sometimes if we factor, I can factor the top. It's a difference of squares. It's a funky looking difference of squares. Sometimes when we factor and we plug in 2 into this factored form, like pretend the function's this instead of that, you could see you get 0 times 2 squared plus 4. This is me plugging in 2. 2 squared plus 4 is 8. 0 times 8 over 0. Now, 0 times 8 over 0 is 0 over 0. However, let's say we could cancel these zeros. What we find is or it's essentially we could cancel these factors. What we find is that the graph that we just saw is actually the graph of x squared plus 4 with one difference. At 2, it's got a hole. So this is a way of like discovering the limit without using your calculator. Now, sine x over x, there's no like non-calculator way of figuring out this limit. I mean, I actually think there is, but I forgot how to do it, and it doesn't matter. This is just more for investigative purposes. If I plugged in 0, I get the sine of 0 over 0. Again, I can't do that. F of 0 is undefined. Your calculator can show that by plugging in 0 and saying, yo, why? Yeah, can't do that. You get 0 over 0, Mr. Mester. 0 over 0 is now 1. 0 over 0 can be anything. Here, 0 over 0 is 8. But what's the limit? Again, don't go crazy, but look to the right and to the left. If you go crazy, your calculator is like, yeah, I just plugged in 0. Oh, actually, you didn't. I wonder how many zeros it'll take before it just plugs in 0. A lot. Anyways, so this is cool. But again, like don't go crazy for other values because it eventually gives up. But here you can see, oh, we're essentially at 1. Let's go to the right of it. I mean to the left of it. Whoops. They're like, yo, you're essentially at 1. Now, I'm not at 1, at 0. I have a hole. You can't see it, but it's there. There's a hole on this graph that you can't see. There's a missing pixel that you can't see. Right there. But we can see we're approaching 1. Okay? Keep in mind this technique for our quiz, finding limits where we have an undefined. We can try to factor to discover the y coordinate we'd be approaching. Keep that in mind. But just show you like how we can see that. Here's a good question, like write a limit statement that explains what this data is telling you. And then what is f of 2? Okay, so I got x's and then y's. My x's, I can see we got values that are getting closer and closer to 2, like 1 to 1.5, 1.1. And then we got y's that are look like they're getting closer, approaching a certain value. Now, f of 2 is undefined, like it says, at 2, undefined. Okay, it does not exist. But as x's approach 2, it looks like my y's are approaching 11 to the left and to the right. Boom. All right, let's look at this one. When x is 5, g, oh, it says g of x, but I says what is f? Change that to g. What's g of 5? G of 5 is undefined. Okay, sure. But I can see two different things. When I'm a little bit less than 5, I'm approaching 6. When I'm a little bit to the right of 5, I'm approaching -1. Write a limit statements. Write limit statements describing what the data is telling me. What the data is telling me is that as I approach 5 from the left of this function, I'm approaching that y coordinate of 6. 5 from the left, 6. But if I'm approaching 5 to the right, 5 to the right, I'm approaching -1. Maybe this is what I'm asking for. That means the limit as x approaches 5 in general of this g function, whatever it may be, that does not exist because the left-hand limit does not equal the right-hand limit. Okay? Now, typically, functions like x squared minus 1, sines, cosines, they're nice. They're smooth. They're connected. There's no jumps. There's no holes. X squared minus 1 just looks like this. Do you need to know that? No. But you do know that there's not like a 0 in the denominator, which will make things funny. We'll talk about that more next class. I like, zeros in the denominator are bad, okay? Not always. They're interesting situations sometimes. But here, x squared minus 1, we're good. It's smooth. I could plug in any value that I wanted for x. Any x I could plug in. I could plug in 2. I could plug in 2.001, 1.999. What would I get? 2 squared minus 1, 3. See? When you have just a simple function that's not crazy, limits are the same as the function values. We're continuous. We'll talk about that more next class. 0. Well, cosine just goes up and down. All right, well, what's the cosine of 0? I don't have to worry about doing anything crazy. Cosine of 0 is 1. Sine, same thing. Sine of 3 pi over 2, -1. Quick little review. Secant, 1 over cosine. What's the cosine of pi over 6? That's a half. Secant, 2. Now, secant does have some asymptotes, but not at pi over 6, so you don't have to worry about it. E to the x when x is pi, right? It's e to the pi. Be okay with that. We won't always get whole number answers. We're going to get some answers that are going to be like e plus blah, 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 blah. And we're just going to leave it, okay? Don't feel like you have to simplify everything in this class. Just get the right thing. I do this with my Algebra 2 students, and it messes them up all the time. I might even change this. I should have put this as -4. Order of operations. Square things first, then make it opposite. This is -16. Now, if I said, and I'm going to throw this in here, this is -4, negative x squared, guess what the answer is? A lot of you are saying, well, it's positive 16, because like a negative of a negative is a positive. Positive 4 squared is 16. Wrong. -4 gets squared first. Then we take the opposite of it, giving us -16. Algebra 2 students make this mistake. Calculus students make this mistake. Here, -4 squared. This is positive 16, -4 squared. All right, this is the jump function we introduced. The way we can kind of tell that it's the jump function. First of all, if I plug in 3, I get 0 over 0. Again, that's bad. But plug in something bigger than 3, 4 or 5. What do you get if you plug in 4 or 5? Well, if I plug in 4, I just get 1 over 1. All right, that's 1. If I plug in 5, I get 2 over 2. All right, that's 1. If I plug in anything bigger than 3, I will get a positive x minus 3 over a positive x minus 3. That's 1. Well, let's plug in something like 2 and 1. Well, if I plug in 2, I have 2 minus 3, which is -1, but the absolute value makes it a positive 1. So I have a positive 1 over a -1. Okay, that's -1. If I plug in 1, I'll have a positive 2 because it's 1 minus 3, which is -2. Absolute value makes it a positive 2. Positive 2 over -2, 1 minus 3. Okay, that's -1. If I plug in any x less than 3, I'll have positive x minus 3 over a negative x minus 3, essentially. And that gives us -1. This is why we understand this with the absolute value as being a jump function. Now the jump function jumps at the x coordinate that gives us zeros. So if I have a 3 here, I'm going to have 1s to the right of 3 and -1s to the left of 3. Left of 3 is -1, right of 3 is 1. Limit does not exist. You will always be quizzed and tested on this jump function, so you might as well know it. Now let me change it up again. What if I put a 4 here? Okay, well, if I put a 4 here, it'd be 4 times 1 over 1. It'd be 4 times 2 over 2. This would change into 4. This would change into 4. I'd have 4 times 1 over 1. 4 times 2 over 2. That would change into 4. That would change into 4. Just a heads up, if you have anything besides just something divided by itself, it just changes what you jump to. This would jump from -4 to +4 rather than -1 to +1. Okay? So that's a heads up in case you see that on your quiz. But the way it's looking like right here, where it's just something divided by itself, we're talking about ones. All right. Now, last couple. If we have situations where if we plugged in 3 like we tried on the previous ones, and we get 0 over 0, undefined. 0 over 0, we'll talk about more class, is an indication that we have like a hole. Now, we didn't like specify that specifically. Like we didn't talk about why. I mean, we did a couple examples in class. We'll talk about more like why. But for now, here's what I'm going to tell you. Like if you ever get 0 over 0, just try to investigate more. Try to see if you can't shake this and maybe make it look different by factoring. Maybe see if you can't realize that after factoring, if you were to plug in +3 in here, that you'd get 6 times 0 over 0. Let's say if you were to cancel those zeros, or if you were to cancel these, you would discover that we are approaching a specific value of 6. This is like the algebraic way of doing what we were doing in the calculator, which was plug in 3.0001. Okay? So same like here. If you plug in your value, and if you ever find that you get 0 over 0, it's an indication that you have a hole. Now remember, like we've done a couple examples, enough examples where we know like holes have limits. They don't have function values. So this is undefined. So we don't have a function value, but we have a value we're approaching. How are we going to figure that out? We're going to factor and like investigate further. What I'm going to do here is factor out a common factor. And then pretending like I'm plugging in 0, that's this x coordinate. We realize, oh, like you get 0 times 3 over 0 times 5. If you could cancel these zeros, if these weren't around, your y value would be approaching 3/5. And that's how we get that answer. Okay? Plug in 3. 0. 9 minus 12 plus 3. 0. This is an indication that you have a hole. Holes have limits. They have a value that they're approaching, but it's like a location that you don't get a value for. You can't plug in 3, but I can plug in things close to 3. An algebraic way to discover the location of the hole is to like investigate further by factoring. if I were to plug in 3, I'd get 0 over 0 times 2. This is a good one because it's like, oh, if this cancels, you end up with 2. It's like, no, if you cancel these, what are you left with? A 1 up top. Like you divide, you have 1 over 1. So if these go away, you don't have like 2 and then like 2, you have 1/2. And you don't have 0. So that's a good one. That's a good one. I think I made sure students messed up on this in my pre-calculus class last year. They didn't realize you had a 1 left over. Yeah, don't fall into the trap though. Put this here for a reason. Don't assume you're going to get 0 over 0. I get 6 over 8. I actually can't factor these. If you tried to factor, you'd fail. This is just like, oh, this is continuous. The bottom's never 0. It's not 0 too. I probably could have picked a different value, but whatever. It doesn't matter. Always make sure you get a whole. Always make sure you plug in and see, do you get a value or don't you? 6 over 8 is the same as 3 over 4. We talked about this in class. I've improved this lesson from the past. I hope this gives you a good understanding of limits. You were introduced to limits last year, starting with piecewise functions. I did it like that. If you were an honors pre-calculus, you had piecewise functions and then you had limits. I think that gives you a good understanding of things. I did it that way this year. Hope you guys know this. We're not going to do that many practice problems before our quiz because our quiz is long. It's like 16 problems. They're quick problems. Most of them are just like look at the graph and write the number. Not that much work, but a little bit of work. So make sure you're ready. Later.